So our extension material for the alkanes, lots of things I could have done, but I thought it would be sort of fun to take the alkane halogenation reaction that you learned back in year 12 and just go a little bit further with it. So for those who came from the straight movie, this is of course how we got here. We're taking butane, we're reacting it up with chlorine, and we noticed that it made 1 chlorobutane and 2 chlorobutane, and it made them in a ratio of 28% to 1 chloro and 72% to 2 chloro. Now, to just refresh your memories, whether you got there from watching the movie in my particular module or whether you remember it from when you went through year 12, the general mechanism is a so-called free radical chain reaction. So start off with a chlorine molecule, gets split apart homolytically, that's a good word, to give you 2 chlorine atoms. One of those chlorine atoms can then bump into a molecule of butane, C4H10, making the butyl radical, because the chlorine grabs itself a hydrogen from the butane, makes HCl, which is one of the products of the reaction, and then the butyl radical there. And then another propagation step, the butyl radical grabs another chlorine molecule, knocks out a chlorine radical, and makes the butyl chloride or the chlorobutane. And of course, this is the general mechanism, whether we're talking about this product being 1 chlorobutane or 2 chlorobutane, because they are, of course, isomers of each other. Now, when you study a reaction in this fashion with these skeletal structures, you've got a lot of unclutteredness about it, of course, but sometimes it makes it a little bit hard to imagine what's going on. So let's go to the full structure of butane to think about this. And I've drawn it as pretty colors here, because essentially we've got 2 types of hydrogens. And remember, it's the hydrogens that are important because it's a hydrogen that gets knocked off, that gets abstracted by the chlorine radical. Okay, we've got the ones that I've colored in red here that are on the end carbons, and this end carbon and this end carbon are indistinguishable. And then you've got the ones that I've got in that sort of pinky color, right, that are on the internal carbons, and again this internal carbon and this internal carbon indistinguishable from each other. So we have 2 types of hydrogen atoms in butane. We have primary hydrogens and we have secondary hydrogens, because the primary hydrogens are attached to a carbon that's only bonded to 1 other carbon atom. That makes it a primary carbon, and these pink ones are bonded to carbon atoms that are bonded to 2 other carbon atoms. That makes them secondary. So we got 6 primary hydrogens and 4 secondary hydrogens. Each of those 6 primary hydrogens is identical because each of these end carbons is identical. Each of those 4 secondary hydrogens is identical with each other but different from the primary hydrogens. So now when we make our free radical, so chlorine comes in, grabs itself a hydrogen. It can grab itself one of the primary hydrogens, making a primary free radical. Again, I've drawn it with this one. I could have taken that one, or that one, or that one, or that one, or that one. All 6 of those red ones are identical. Alternatively, chlorine coming into a butane molecule can take one of the pink ones, one of the secondary hydrogens, making a secondary free radical. Okay, now these free radicals are, you could call them intermediates in the reaction. Okay, they're made in one step and then used up in another step. And a lot of time when you're studying mechanistic chemistry or trying to explain an observation, you want to have a look at what intermediates are formed, because the more stable the intermediate, the more likely it is to be formed, the better the reaction. So anyway, we've got our choice of our 2 free radical intermediates. At this point, of course, they go into this one, they find another chlorine atom, chlorine molecule, grab a chlorine off there, and so we either make the 1 chlorobutane here, and there's 6 possible positions we could have used for that, because the radical can be there, or there, or there, or there, or there, or there. So 6 hydrogens, right, that could have been lost all the way through to give us 1 chlorobutane. Only 4 ways in which we could have made a 2 chlorobutane, that is, one of the pinky hydrogens gets first of all removed to make the secondary free radical, and then the chlorine comes in to fill that spot. Okay, so what we should have expected here is we should have expected, if all else were equal, there to be a 60% of the 1-chlorobutane and 40% of the 2-chlorobutane. 6 possible ways to get to the 1-chloro, 4 possible ways to get to the 2-chloro. However, not only did we not have more chlorobutane, 1-chlorobutane and 2-chlorobutane, we had a significantly much more 2-chlorobutane than 1-chlorobutane. Okay, so we got much more 2-chloro than we would have expected, much less 1-chloro than we would have expected. And we can trace that back to these free radical intermediates. You make the 2-chloro or the 1-chloro from the free radical, either the secondary free radical or the primary free radical. And whichever free radical is better is going to be more likely to be made and thus react. So what we can say from this observation is that the secondary free radical must be much more stable than the primary free radical, because we end up making more of the secondary than we do of the primary than we otherwise would expect. Let's do another example. Let's take the isomer of butane, 2-methylpropane. Okay, so again, you've got 4 carbon atoms. You can see those in this rather horrible skeletal structure. But anyway, react that with chlorine, shine light on it, and we can either make 1-chloro-2-methylpropane, or we can make 2-chloro-2-methylpropane. Okay, so either the chlorine goes on one of these primary positions, or it goes on to this would now be a tertiary position. 63% of the 1-chloro, 37% of the 2-chloro. So you look at that and you say, oh, remembering how these come from the free radicals, this free radical must be better than this free radical. Not so fast. Let's go and have a look at the much more detailed full structural joining here, because this pictures actually tend to lose an awful lot of the stuff. So here is our 2-methylpropane, right? There's 1, 2, 3 carbon atoms with the methyl group coming off here at the 2 position. Now, if you look here and you assign the types of carbons and thus the type of hydrogens, each one of those methyl groups is indistinguishable, which means that each of those hydrogens that I have in the red are indistinguishable. So there are 9 primary hydrogens and only 1 other hydrogen that in this case is a tertiary hydrogen, because it's bonded to a carbon that's bonded to 1, 2, 3 other carbons. Okay, now this is a great illustration of what I said in the very first movie of the main sequence, that while you lose an awful lot of detail when you go to these skeletal structures, right, you also don't have too much stuff clogging you up. A lot of times, most of the time, the skeletal structures are better. There are times, however, in which going back to the full structure is better, even if you have to do what I had to do here, sort of stretch that bond there so that these hydrogens could actually be seen. Anyway, 9 primary hydrogens, all identical, 1 tertiary hydrogen, identical. Let's do that first step. So going to the free radical. So we got a primary free radical we could make by taking away one of the red hydrogens. We have the tertiary free radical that we would make by taking away this 1 tertiary hydrogen. Primary free radical will go on to make the 1-chloro-2-methylpropane, and remember there are 9 positions for this. Whichever one of these red hydrogens I'd taken, I would still make 1-chloro-2-methylpropane. Tertiary one will make the 2-chloro-2-methylpropane. There's only 1 possible position for that. Okay, so 63% of the 1-chloro, 37% of the 2-chloro, but one would really expect 90% of the 1-chloro and only 10% of the 2-chloro. So even though there's more 1-chloro than 2-chloro, there's still less 1-chloro than you would expect and more 2-chloro than you would expect. Less that came from the primary free radical, more that came from the tertiary free radical. Now let's wrap this up on this slide, in which we do a little bit of maths. Let's go back to the first example where we took butane and we made either 1-chlorobutane or 2-chlorobutane, because there were 6 primary and 4 secondary hydrogens there. We expected 60% or 0.6 of the 1-chloro, 40% or 0.4 of the 2-chloro. We actually saw 0.28 and 0.72. Now, that means that the relative formation, the relative rate of formation, because it is a kinetic process, is equal to, first of all, the ratio that we actually saw, 0.72 over 0.28, divided by the expected ratio, right, which would have been 0.4 over 0.6. Well, when you divide by a fraction and then flip it up, you can multiply it. So that just becomes, instead of 0.72, 0.28 divided by 0.4 over 0.6, it becomes 0.72 over 0.28 times 0.6 over 0.4, which is 3.9. So based on these numbers now, the secondary one, that's this one, 3.9 times more likely to form, 3 times better kinetically to form than the primary one, the 1-chlorobutane. Okay, not just taken from what we observe, but comparing what we observed to what we should have observed. Now with that, let's talk about the chlorination that we saw for the 2-methyl propane. And again, we can get the primary one, 1-chloro, or the 2-chloro 2-methyl propane is actually now a tertiary one. 9 primary hydrogens, so expect 90% or 0.9. 1 tertiary hydrogen, so expect 10% or 0.1. We actually observed 0.63 over 0.37. Do the same calculation, and what we find is that even though there was more at the primary made than the tertiary made, because we expected 9 times as much to be made and we saw less than 2 times as much has been made, that means that the tertiary is 5.3 times better, 5.3 times faster than the primary one. So putting that all together, for chlorination, if you have choices of where you will chlorinate, if there's a tertiary one, it's 5.3 times better than a primary one. If there's a secondary one, it's 3.9 times better than a primary one. If we go and look at the brominations, however, we see a much more significant effect. Tertiary, 1,640, secondary, 82, primary, again, relatively 1. The reason for that is because the brominations generally happen more slowly than the chlorinations do. That means there's more time for the molecules to think about, and this is silly, kind of, assigning human characteristics to molecules, but it kind of works, right? It gives more time for the molecules to think, well, what's my more stable situation? Tertiary free radicals are much more stable than secondary free radicals, which are much more stable than primary free radicals. Now, how do we use this? Well, that means that if you want to make an alkyl chloride or a chloroalkane, you're only going to use this method if all the hydrogen atoms are equivalent. Okay, because yes, there is some distinction between the secondary, the primary, and the tertiary. It's not a huge amount of distinction, not a huge amount of so-called regio specificity. So if you want to make chloromethane, you might take methane with the right amount of chlorine in it and make it. But on the other hand, if you want to make 2-chlorobutane, yes, you could make more of it than the 1-chlorobutane if you did the reaction, but you still got a rather inefficient reaction. On the other hand, if you want to make a tertiary alkyl halide, you would make the tertiary alkyl bromide or the tertiary bromoalkane, because look how much better the tertiary bromination is than the secondary or the primary. Anyway, there was your extension. Some of the problems on this are kind of fun, at least I find them fun, talking about all the different monochlorinated ones you can make, and also talking about some of the different rates that we've seen associated with this last slide. Hope you enjoy it. Bye-bye.